Yes, good afternoon, everyone here. Today my topic is Hermite cosh Gaussian laser-induced electron acceleration in vacuum, basically. Recently, this work is published in Laser Physics Letters. So I'm briefing this work, what we have done in this paper. And first of all, I will discuss what is the basic principle of electron acceleration, and then what is the dynamics, electron dynamics with this Hermite cosh Gaussian laser beam. What are the applications of the same, and then I will discuss the results and discussions followed by the conclusions. So first of all, we can understand that accelerator is a device which is used to produce a beam of charged particles, for example, electrons or protons here. And we can accelerate these particles with very high velocity in the range of multi MeVs or GeVs, provided the particle is having a nearly constant velocity or energy here. The parallel trajectories are there, and we have the small beam cross section for the laser. And to deliver these particles where they scatter from the target, this is important to reveal the structure of the constituents and to create the new particles for the study. For example, gamma particles or other things. So how the laser, first of all, can accelerate the electrons. So we can basically understand with the wave particle interaction. So this equation is applicable over here. We can understand this as the strongest interaction of the charged particles with the wave will occur only when this velocity of electron is equal to the phase velocity of the wave. In that case, if this condition is satisfied, then the electron can resonantly interact with the wave. And in that case, the Doppler shifted frequency of the wave will be equal to that of the electron. So in this case, only the particle can gain energy, and thereafter it may saturate the energy also. So these are some preconditions, prerequisites for the energy gain of the electron with the help of laser. The number one, we can see that the laser can exert a longitudinal force on the electron, and its phase velocity is close to the velocity of the accelerating electron, so that the wave field appears quasi-static to that of the electron. And in that case, what will happen? The efficient energy is transferred to the electron from the wave. So these are very interesting applications of the particle accelerators. For example, across our daily lives, we can see television, a computer monitor, microwave oven, oscilloscopes, or in industries. We can see the applications in the food sterilizations, electron microscopes, radiation treatments of the materials, nuclear waste treatments, and of course the medical applications here, most important in case of cancer therapy, radiology, instrument sterilization, isotope production, and here recent research is going on with the high energy physics experiments, a light source for the chemistry, biology, etc., with the optics and the neutron sources. So these are the interesting medical applications. Yeah. So basically, whatever the work we are doing in the case of laser-induced accelerators, this is commonly used in the therapy and imaging, isotope production for imaging. A lot of work is going on in ELI, Hungary, ELI seized. So we can discuss that. So benefit of this laser profile which I have taken, that is radially polarized Hermite cosh Gaussian laser beam for the electron acceleration. Why we have used this profile? So we can understand that in the laboratory, we can create this profile using the Gaussian laser, Hermite Gaussian laser, or cosh Gaussian laser beams. So as a result, we can say that the Hermite cosh Gaussian beam is a generic kind of beam which encompasses all the above beams. It has the properties, some properties of all the other beams also. And moreover, the Hermite cosh Gaussian profiles have a lot of benefits or advantages in the laser plasma interactions. For example, they have the more adjustable parameters like Hermite polynomial, mode indices, or decentered parameter of the laser, so that we can control the laser beam for the electron acceleration. So in this case, we have investigated the electron's dynamics. We have seen the electron velocity, energy, other things, profiles, employing a radially polarized Hermite cosh Gaussian laser beam. And due to the property of the beam, it has a interesting property that it can focus earlier as compared to the other laser beams, so that we can say that it is better suited to acquire the higher energies, for example, GeV order energies over a shorter period of time than the other laser beams. So the main parameters which are responsible to get the higher energy beam, higher energy electron beams is a decentered parameter of the laser, Hermite order, or intensity parameter, and the beam waist width, R naught dash. These symbols we have chosen in the paper. So this work is a theoretical work here. I have solved the numerical equations, then I have normalized the things, then we have done the simulations. So we can understand this equation number 1. This is a simple electric field profile for this radially polarized Hermite cosh Gaussian beam, where we have two components, and we can see that the transverse component is given as this, where E0 is the amplitude, HS is the order, this under root 2R, beam waist, initial spot size, decentered parameter B, and these things are there. So longitudinal component I have derived from this equation number 2. And this equation we have taken, that is called the Newton-Lorenz equation. So from this equation, we have calculated the force on the electron by the laser, and then we have calculated the electron's momentum, how it is going, what is the energy. So these are the momentum components of the electrons under the influence of this force. So from this equation number 4, I have resolved the components in the other directions, R, Z, for example. And then after, from the momentum equation, these two equations, I have derived the energy. This is gamma. Gamma is the energy gain for the electron. It is a Lorentz factor basically. So which is equal to gamma square is equal to 1 plus px square plus py square plus pz square. So I put the value, and then I have calculated this change, the change in the energy. Gamma dash is a normalized one. The dash means I have normalized all these components for the numerical values. So this is your energy gain of the electron, and these are the velocity components of the electron in the transverse and the longitudinal direction here. So then I have plotted these equations by using the softwares MATLAB and Mathematica, and I come up with these results. So we can see that this is our electron energy gain, that is gamma in MeVs. This is my normalized time T dash, and we have seen that the electron is acquiring the higher energy gain. Not only acquiring, but this energy gain is saturated also. This is very important thing because energy is gained resonantly. Resonant interaction of the laser and electron takes place. That is why after this part, the energy got saturated, and we can use this energy in some applications. So this is the variation of the laser initial spot size. Here it is in micrometers, and we can see that as the spot size is increasing, the energy gain is also increasing. But the thing is, this energy is saturated after some time. So it is a property of this laser. We have observed this value. Similarly, in the second graph, we have seen the effect of the decentered parameter of the laser. And this is intensity of the laser, initial intensity of the laser. This is kept fixed. This is the spot size I have taken, the optimized values. And with these optimized values, with these optimized set of parameters, the gain is almost, we can see that 8,000 MeVs for this value, decentered parameter 2. And similarly, for this decentered parameter 0.5, our energy gain is almost 1700 MeVs. In the next graph, we have changed the decentered parameter, the order, and then we have seen the results. The results are, in all the graphs, the energy is saturated. So this is a very important thing here. In the fourth figure, we have changed the intensity of laser. What will happen if you increase the intensity, decrease the intensity? What type of parameters are required to get the effective energy gains? Not in all the optimized values we can get the efficient energy gain. It is not there, so we have to check the various parameters. And in this case, we can see that for the initial spot size equal to 10, decentered parameter equal to 1, S order is equal to 3, we can achieve a quite interesting energy gain, efficient energy gain. And in this case, I have seen the effect of the initial spot size on the maximum energy gain. Here we have the gamma M as a maximum gain it can achieve. And we have also seen the effect of two different profiles, linearly polarized and the circularly polarized. So this is my new work, which is submitted in optical and quantum electronics. We are still doing this work. We are looking for the linear polarized and circularly polarized Hermite cosh Gaussian beam, and we are comparing these two. So we have observed that circularly polarized beam is more efficient as compared to a linearly polarized beam for the electron acceleration. So from this overall paper presentation, we can conclude that this profile, Hermite cosh Gaussian profile, is called a golden profile also, because it has a property of self-focusing, and which is allowing the electrons to be easily captured, and acceleration is done up to the order of GeVs, which is highly crucial, which is ideal for the future research. And if we choose the correct parameters, for example, correct laser intensity, beam waist, decentered parameter, Hermite order, we can achieve energy up to 8.43 GeV without using any kind of external frequency variation or external magnetic field. So as a result, we can say it as a golden profile. So this work is done with the collaboration of Professor Arvinder Singh from NIT Jalandhar, Punjab, and Professor Nitikant from University of Allahabad. And I'm very thankful for the fruitful discussions and contributions in this work. And I'm also thankful to my university, lovely professional university, and NIT Jalandhar, from where I have done my doctoral. So that is all for today. Thank you very much for your attention.